SPWM result. Actually, there are actually two problems for the result. One is that it has some circles for the result, so we can change the scope. Yeah, I think it's because of the scope setting. So let's use the scope and log the data time to IG. And now we can run it. Okay. Yeah. Oh, and we can see, yeah, it's better, and because there's no circles for the data points. Yeah, and it's around 10 ampere. Yeah, but this waveform is not that smooth. Why? There is another setting. So it's because of the step size. Actually, we need to make the result more precise. So we will decrease the sample time or the step size. Yeah, so it's we change it to 0.1 microsecond. But now when we run it, it will take longer time. Yeah, it will take longer time. We can see it's much slower. It's much slower. All right, and now let's have a look. Oh, okay, yeah, this result is closer to a sinusoidal waveform, and you can perform the FFT to see the harmonic components. Yeah, but it has already been filtered out. Most of the high order harmonics has been filtered out by the air filter. So yeah, the THD should be around 10%. And so that's the unipolar SPWM. Then we will continue with the bipolar SPWM. So if you remember, as we discussed in the class, the bipolar SPWM actually has easier modulation technique because we only need one. Yeah, so the left hand side is unipolar. Then the bipolar, we will just need to use one reference, compare with one carrier waveform with one carrier waveform. So the reference will be the same. We do not need to change it. But for the carrier waveform, if you remember, we need to change it from 1 to -1 and then to 1. So it switched for so bipolar. It switched from 1 to -1 and then to 1. And we just need to compare these two. Compare these two. And then we are able to control all 4 switches. So we will, yeah, so first we will just disconnect them because these signals, 1 and 4 will be operating together, and 2 and 3 will be complementary. It will be turned on and off complementary. So 1 and 4 results, and 2 and 3 we will need to use a NOT. 2 and 3. All right, and then we just need to run it. Run it, and yeah, first we can have a look at the, well, yeah, like the frequency is too high, so it's hard for us to analyze it. Let's decrease the switching frequency. Let's change it to 1K, like we did in the unipolar. Yeah, unipolar, at first we use the 1K. So here we will also use the 1K, 1 kilohertz. Now it's slower because we change the discrete time. And yeah, we can see it's a bipolar from positive 200 to negative 200. And we can see it's also same as we discussed in the class for the bipolar SPWM. And then we will perform the FFT. Double click FFT, the VAB update, and the maximum frequency. Okay, compute FFT. Yeah, and we can see this is actually the bipolar SPWM, and we can see for unipolar SPWM there is no harmonic component right at the switching frequency, but here we can see for the third order of the switching frequency, or the odd order, yeah, odd number of orders. Yeah, for example, like 1 kilohertz, there is the component. 3 kilohertz, there is component. 4, 2, there isn't. 5 kilohertz, there is a component. 7 kilohertz, there is a component. And there is also the component, yeah, like this is yeah, plus and minus 120. So this is like 1 kilohertz plus minus 120. You can see that's the side bands. This also has a side bands. So actually this THD is a kind of different. It's kind of different. And we can see the THD is higher than that in the unipolar SPWM. That's also what we discussed in the class. The bipolar SPWM has higher harmonics than unipolar SPWM. Yeah, that's because it can make the current increase and decrease like larger current ripples, right? Yeah, it has higher THD. So that's a bipolar SPWM. And all right, to make it consistent, we can also have a look. Yeah, now the current waveform is actually really bad because it has the higher current ripples as we discussed before. So we need to increase the switching frequency. Yeah, to 12 kilohertz. So 12 times. Yeah, from 1 kilohertz to 12 kilohertz. Now I think this is we can not see anything. Now for the current. Yeah, for the current, yeah, we can see it's now like when we increase the switching frequency, the current is much better. It's much better. But here there's actually one problem. The current actually it will increase, keep increasing, or like being divergent or diverge. The current diverges. Now, why is that? Because this circuit generally it does not have the damping or the resistance. So generally, to solve this problem, it's a better way is, for example, we use a damping, for example, like 0.04 ohm. You can also change the resistance to C, and let's try the 0.4 ohm. Add a damping to the system so that it will not become unstable. Yeah, because this system has a sinusoidal voltage. That's like a disturbance. Sinusoidal disturbance is a second order. So yeah, now let's have a look at the current results. It's still like increases, but it's better if we put the stop time from 0.1 to 1. Yeah, we can. Yeah, it also takes time. So yeah, if we have a longer run time, we can see it's more clear. Yeah, to see if it really become unstable. Yeah, actually, the scope here. Yeah, we can see at the beginning, it like increases a little bit. Yeah, there, or we can say at the beginning there is some oscillation, but after some time, it generally becomes like stable, and I think the yeah, actually after 0.3 seconds, it should become stable. It becomes stable. Yeah, and we can stop here. I think we can stop here. And or yeah, we will just take the later time. Yeah, and we can see the harmonics is actually larger than the unipolar SPWM in unipolar SPWM, but the amplitude should be correct. Yeah, the current is like 10 amperes, and we can also perform the FFT on it. So FFT. Yeah, if you remember, like you can double check the IG for unipolar. So start time, let's use the maybe 0.2 is better, or 0.3 or 0.4. 0.4 is even better. Yeah, okay, 0.4 could be more accurate. Compute FFT. Yeah, we can see the THD is still like 23 something. It could be double than the unipolar SPWM. So that's the bipolar SPWM. It has a disadvantage that it has larger harmonics, or more harmonics, a larger THD value. So that's generally the bipolar SPWM. Okay, we will continue to the double frequency unipolar SPWM. So for the double frequency unipolar SPWM, if we still remember, we will, it's kind of also similar to the bipolar. Instead of using just one reference, we need to have two references. So that's one reference compared with the wave, and to control the leg 1. So that's G1 and G2. Then, okay, so this will be compared to, we have that. Yeah, this two will be compared to control G1 and G2. G1 and G2, leg 1, leg A. And then we need to use the same thing. So, but now we need to flip the sinusoidal waveform. So we need to, can we just like connect it to the knot? I don't think so. We need to, let's multiply it by -1 to be safe. So let's multiply it by -1. Multiplied by -1, and this reference is used to control the leg B, and we can run. Okay, yeah, I think we do not need the stop. The run climb, we can change to 0.1 to make it faster. Oh, and maybe we do not need the resistance at this time. But anyway, we can check it first. You see, yeah, and we can see like we can see the harmonics is much smaller, right? And anyway, we will for unipolar, we may not need the resistance, so it's just the inductance. Right, finally, okay, cool. This result looks very good. Yeah, and we can also have a look at its FFT. It's FFT update. The IG. Yeah, it should be smaller than the smallest should be. 0.0. Yeah, it's like 6%. Like 6% should be the smallest. And yeah, if we want to compare with the unipolar and bipolar for the 1 kilohertz, we can also have a look at the the 1 kilohertz results. Yeah, so in this way, we can have a look at the output voltage for the double frequency unipolar. Yeah, so this is a double frequency unipolar. And we can also have a look at its FFT. Yeah, we can have a look at the waveform. I think the IG for the grid current is updated. Yeah, it become worse because we decrease the switching frequency. And let's say VAB. And we can have a look at the harmonic component. Yeah, and we can see there is same as the unipolar. There is well, it's actually there is no switching frequency component even. Yeah, or the sidebands around the odd number switching frequency because it's double frequency. Yeah, it's double frequency unipolar. So only has even though the carrier waveform or the switching frequency is 1 kilohertz, we only have the harmonics around 2 kilohertz, 4 kilohertz, 6 kilohertz, 8 kilohertz. Yeah, there's no harmonic component at the 1 kilohertz or 3 kilohertz. That's the switching frequency. So that's the double frequency unipolar SPWM. All right, so that's generally the simulation for the project, for the power electronics project. Yeah, and I hope you can write the report for what you have learned during this project. So that's all about the tutorial video, and thank you very much.